those very kind introductions. Oh, let me do this.
Turn it on.
Yeah, I'm not so smart when it comes to certain things. At any rate, thank you so much for those very kind introductions. So I'd like to tell you about how I got started and go up to some of the work we're doing today and give you an overview of some of what we've tried to do. So I'm a chemical engineer. I got my degree in 1974. And when I got done, pretty much all my friends went to work in oil companies. They had many job offers. So I thought I'd do exactly what everybody else did in my class. And I went to these companies, and even though you heard I got a lot of rejections, I didn't get rejected from oil companies. I got 20 job offers, four from Exxon alone. And believe me, I wasn't very good. But they just had so many openings. So, but when I was there, some of them would tell me, well, gee, if you could just increase the yield of this one chemical by 0.01%, they said that would be great, it'd be worth billions of dollars. But I remember flying back to Boston thinking I didn't want to spend my life doing that. And I kept thinking, how could I use my background to maybe make an impact in the world? And one of the things I did when I was a graduate student is I helped start a school for disadvantaged high school students, and I developed some new chemistry curricula. And so I started, one day I actually saw an ad to do just that and do research at City College of New York. So I wrote them a letter applying for a job, but they didn't write me back. But I liked those kinds of ideas, so I applied to another, say, 40 schools, and none of them wrote me back. So that wasn't going so well. So I started to think, what other way could I use my chemical engineering background to help people? And I thought about medicine. So I applied to a lot of hospitals and medical schools. And as you heard, they didn't write back either. So one day I was walking into the lab, and one of the older scientists said, he said, Bob, there's this surgeon in Boston named Judah Folkman. And he said, sometimes he hires unusual people. He thought very highly of Dr. Folkman. I won't say what he thought about me. But Dr. Folkman had this idea that if you could stop blood vessels, you could stop cancer. And so, and in particular, he said it's a chemical signal that he called TAF, or tumor angiogenesis factor, that did that. And I just thought that was a great idea. I really was interested in that, and I really liked him. So I ended up taking a job there. But the biggest problem that was faced was there was no way to really study blood vessel growth. So one of the things I had to do, or that I was interested in doing, was developing what we call a bioassay, a way to study blood vessel growth. And to do that, you need sites where there are not very many blood vessels, but also a lot of the molecules that I was studying were very large molecules. So, I mean, just to give one example, we were thinking about developing an assay in a rabbit eye, which normally had no blood vessels, but the tumor will cause those vessels to grow. But what I wanted to develop was a tiny polymer system, a tiny drug delivery system, that you could put in the eye or other sites of the body that could deliver any of these large molecules. And so we wanted an assay like that. So we looked in the literature, and I asked a lot of people, a lot of very good chemists. In fact, we even asked Nobel Prize winners in polymer chemistry, but they all said that you couldn't really do that because if you took a tiny system and you encapsulated something big in it, it just wouldn't be able to get through any more than, say, we could get through a wall. Nonetheless, if we were going to solve this problem to create the bioassay, I had to solve this problem. So I spent 2 years working in the laboratory, experimenting with different materials, different techniques, and I found over 200 different ways to get this to not work. But eventually, I found a way to get it to work, and we were able to make these little particles. You see a picture of one, and one cut in half. And we published, as Maria had mentioned, in the journal Nature, and this is a graph from it, that you could deliver, really all kinds of large molecules. It's also, to my knowledge, the very first time that nucleic acids had been encapsulated in tiny particles and shown to be delivered. I want to go back to 3 months before this paper came out. I was 27 years old, I got asked to give a talk at a Midland Macromolecular Symposium. I was very nervous. I practiced this talk for about 2 weeks into a tape recorder over and over so finally the day came, and I got up and I gave the talk. And I thought at the end of it, I didn't do that badly. I didn't forget too much what I was going to say. I didn't stammer that much. And so I thought when I was done with this talk, all these older chemists and engineers, being nice people, would want to encourage me, this young guy. And when I got done, I stepped off the podium, and a whole bunch of people came up to me, and they said, "We don't believe anything you just said." They said, again, that the molecules were too big, and also the solvents I was using, like methylene chloride and ethanol, they would destroy whatever we put in. And actually, things went downhill from there, if that were possible. I tried to write research grants, and like the NIH, National Institute of Health. My first 9 were rejected. What they would say is, this is pathology study sections, and they'd say, well, Dr. Langer is a chemical engineer. He knows nothing about biology, and even less about oncology. Now, I thought I knew enough about math to know that was hard to do, but anyhow, I didn't get any of those grants. And I really liked working at the hospital. I was actually the only engineer in the entire children's hospital, but I really liked that. But a lot of my friends said it's probably not good to do that forever. So I applied for faculty positions, and I'm a chemical engineer, so I applied to those chemical engineering departments. No chemical engineering department would hire me. So I finally got a job in a nutrition department. The reason I think I got it was because the head of the department, Nevin Scrimshaw, he was a benevolent dictator kind of department head. And so he offered me a job, but he didn't ask anybody else in the department what they thought. Which might have been okay, except for one thing, which was the year after I joined the department, he left. And so a lot of the senior faculty decided to give me advice, and their advice is I should leave too. In fact, one of my good friends, Mike Marletta, who later became head of Berkeley's chemistry department at Scripps, a number of years ago, he was giving a talk when I won something, and I just took a quote from it. He said, one evening I went to a faculty dinner at a Chinese restaurant with, he was referring to 1979. I went to a faculty dinner at a Chinese restaurant with myself and some senior MIT professors. He said, a senior scientist sat quizzing us while smoking a cigar. He said, when the older scientist heard my concepts for drug delivery, he blew a cloud of smoke in my face and said, you better start looking for another job. And Mike said he thought it was in a Fellini movie. So that wasn't so good. But fortunately, I'm still at MIT. I don't like to give up that easily. And I thought, continued to do work on the drug delivery systems, and we'd done them well enough so that I thought we could use them to create those bioassays that I mentioned. Let me just give you a warning before I show the next slide, because it's very bloody. I showed you eyes. Now I'm going to show you blood vessels in them. We took 99 fractions almost and tested them of macromolecules, and 98 didn't work, but one did. And this was actually very exciting to us because it proved for the first time that blood vessel inhibitors did exist. We published this in the journal Science. If you look on your left, you see what happens normally. We repeated this experiment. I was working with several surgeons over 1,000 times, and you always get these sheets of blood vessels, and the tumors always get big. But with one of the fractions, and we repeated this 21 times, you get the vessels are sparser, they're lower, they avoid the tumor. So we published this in Science, and it also would provide a pathway for people to isolate all future blood vessel inhibitors, and actually lots of other informational macromolecules. Nonetheless, medicine, is, as you may all know, is a very slow process. It took 28 years from this paper before the first blood vessel inhibitor was approved by FDA. But starting in 2004, 28 years after this paper, using techniques we've developed, Genentech would develop the first FDA-approved anti-cancer, anti-blood vessel drug, which was Avastin. That's probably the number 2 or 3 best-selling biotech drug in history. But what was striking is you keep seeing, and this isn't even a complete list, many, many blood vessel inhibitors being approved by FDA, including 4 even last year. And not only that, not only are they used for all kinds of cancer, they're also used for diseases of blindness in the back of the eye. Well, going back, like Lucentis and Eylea, going back to the 1970s, one of the things we also wanted to do was file a patent. Children's Hospital never had a patent, so filed for one for the first time. 5 years in a row, it got rejected by the patent examiner. And I remember the head of the hospital coming to see me, he said, Bob, you gotta just quit. They're never gonna allow this patent. But I don't like to quit, so I started to think, how could we convince the patent examiner to allow this patent, legally, of course? And science wasn't really working. But as I told you in the beginning, lots of people told me this was impossible, it could never work. I wondered, maybe somebody wrote that down. So in 1982, I did what's called a science citation search to see who cited that Nature paper Maria mentioned. And I found, I had no idea this was written, but I'll just read it to you. This was a 1979 paper I found in 1982. They said generally the agent to be released is a relatively small molecule with a molecular weight no larger than a few hundred. One would not expect that macromolecules, for example proteins, could be released because of their extremely small permeation rates. However, Volkman and myself have reported some surprising, so I thought surprising, that's a really good word for patent examiner, that clearly demonstrate the opposite. So I showed this to the people at the hospital. They flew down to Washington to show it to the examiner. And he said, gee, I had no idea. He said, if Dr. Langer can get written affidavits from each of these 5 people that they really wrote this, he'll allow the patent. So I wrote them. They were all nice enough to write me back. They really wrote it. And we got this very, very broad patent. Also, over those years, our lab had done a lot of work on understanding the mechanism of release, the fundamentals of release from these, which was creating very tiny tortuous spores that go all over the place inside these materials, and even develop mathematical models for predicting all this. And so with that, and with these patents, we got involved in teaching companies how to do this, and licensing things, and even starting companies myself. And actually, Maria did a much better job in her introduction, saying all the different things they've been used for. But these are pictures of them. I mean, and if you didn't have these systems, a lot of these drugs wouldn't work. Like, you see Lupron Depot there, which Takeda developed. We had an arrangement with them. And that is a peptide. And if you can't swallow it because it's too big or take it nasally, if you inject it, it's destroyed just like that. So they put it in little microspheres, in this case, that you can inject under the skin. And now you can make it last for 1 month, 6 months. And there are many, many others out there for treating all the many different diseases that Maria mentioned. And I even had this fish tank on the bottom because it turns out Yanni Zohar, who I work with, came up with these ideas where you could actually use this to induce spawning. And now it's used in pretty much every fish species in aquaculture, which turns out to be a $250 billion industry. And you can even take fish that are really endangered and keep them alive and amplify them over time. So that's kind of how I got started, even though some of this goes up today, but new companies keep making new delivery systems and drugs every day. But one of the things that I wanted to say is, since I worked on materials, I began curious and also had an appointment at the hospital, how did materials find their way into medicine? I thought naively, as a lot of what I've done has been pretty naive, I thought it must be older chemists or older chemical engineers that were responsible for creating the materials. But I found out that was almost never true. What I found out was pretty much every time a material found its way into medicine, it was a medical doctor going to their house and finding an object they wanted to use. So in the case of the artificial heart, back in 1967, some of the clinicians, they said, well, what object is kind of like a heart? And they said, a lady's girdle. That's a good flex line. So that's what they put, that's a polyether urethane. So that's what they put in the artificial heart in 1967. That is still what's used today in 2023, because once you start down that process from a regulatory standpoint, FDA type standpoint, it's very hard to change. And the artificial heart doesn't work that well. Blood hits the surface of the artificial heart, and it can form a clot, which can go to your person's brain, and they get a stroke and they die. But if you think about it, something that was designed to be a lady's girdle, it may not be the optimal blood contacting material. And breast implants, one of those was a mattress stuffing. And this is only a partial list. So I thought, being a chemical engineering, you could do maybe what's called chemical engineering design. And rather than take things from your house, maybe you could ask the question, what do you really want in a biomaterial from a chemistry standpoint, engineering standpoint, biology standpoint, and synthesize it from scratch? Let me give one example and maybe a second. So when we started, there was only one family of polymers, the polyesters, that had been approved by FDA. They dissolve like this. It's kind of like what we call bulk erosion. They start out like a phone book, get spongy and fall apart. That's okay for some drugs, but if you had a toxic drug like insulin or an anti-cancer drug, it could be fatal because it would just dump out. So we said, from an engineering standpoint, you really like to have this, surface erosion. So how do you do that? So you ask different chemistry and engineering questions. First, what do you want to cause, if you're going to design it from scratch, what do you want to cause the dissolution? Well, it could be an enzyme, could be water, something else. But everybody has different enzyme levels, and also the enzyme levels around any material change over time in the body. So that may not be very reproducible, and it isn't. However, if you pick water as the catalyst, we all have excess water. So we said, let's make it dissolve because of water. This is a very simplistic slide, but there's no, it just shows polymer schematic monomers connected by bonds. So then we said, if we do that, and we make water the catalyst, we're going to want the monomers to be very hydrophobic, water repellent. And then we said, but we need to dissolve fast enough, so we need to figure bonds with the right lability. So we went to organic chemistry and selected anhydrides, and had this idea of making hydrophobic polyanhydrides. And what we did is I got in the same room some very good polymer chemists like Gary Winnick and very good chemical toxicologists like Mike Marletta, who I mentioned before. And we tried to say, well, what, and we wrote this on the blackboard, what should be the right monomers? And just one example was we picked sebacic acid and carboxyphenoxypropane as a copolymer. And our thought was not only did these look on paper to be safe, but also by changing the ratios, maybe we could get different erosion rates. And that, in fact, turned out to be true. If you change the ratio of those two, you can go with a millimeter thick slab. If you use all carboxyphenoxypropane, that's the 0%, it'll probably take 3 or 4 years for that to dissolve. But if you put 79% sebacic acid in, it's all gone in 2 weeks. So you could simply dial in the ratios of these and make them last almost any length of time you wanted. And if the drug loadings are low enough, the drug release will follow those. So one of the things, like for me, I love doing the basic work. I love coming up with these things, and writing the papers with my students. But I also really wanted to see what we did make a difference in human lives. And I learned, as I was saying to some people at lunch, that if I was, we could write these papers, but that didn't mean anybody was going to take it up. So so in this case, Henry Brehm, who was a young neurosurgeon, came to visit me. He's now chief of neurosurgery, at Johns Hopkins. But he wanted to come up with a better way to treat this disease, glioblastoma multiforme. And when he came up, the only drug that was used was BCNU. And it's a very toxic drug, travels throughout the body, and causes a lot of bad side effects. So he and I thought maybe we could come up with a new paradigm. And that is, he's going to operate on the patient anyhow to take out the tumor as much as he can. But before he closes the patient up, what we thought is maybe he could put in these little wafers and that could locally deliver the drug to the tumor. And normally the drug lasts 12 minutes, but if it's put in a polymer, he said he'd like it to last for a month. We could do that by picking the right ratios of those monomers. And also, the other thing, which is the fourth bullet, is you're going to get high concentrations in the brain and low concentrations in the rest of the body where it could cause harm. Now, if you get an idea like this, of course, when you're in academia, you have to raise money. So I would again write grants to the NIH and so forth. And we did absolutely terrible. I saved some of the reviews. When we first wrote this grant, the reviewer said, well, you won't be able to synthesize the polymers. But I had a very good graduate student, Howie Rosen, who later became president of Alpha Corporation, a $12 billion corporation, and was elected to the National Academy of Engineering, and he synthesized them. We sent the grant back again, and the reviewer said, well, that's good, but you have anhydride bonds that there's certainly, the polymers will react with whatever drug you put in. But Cam Young and Bob Linhart, both of who got elected to different national academies, professors at Columbia and RPI now, showed that didn't happen. So we sent it back again, and the reviewer said, well, okay, that's good, but the polymers are low molecular weight, they're fragile. So Avi Dohm, who's now the dean of pharmacy at Hebrew University, and Edith Mathias, who's a full professor at Brown, they showed that you could make really strong, high molecular weight polymers by using the right chemistry. Sent it back again, and the reviewer said, well, yeah, that's okay, but these are new materials, they're certainly going to be toxic. I had another graduate student, Cato Lorenzen. He later became Dean of Medicine at University of Connecticut, and he actually won the National Medal of Technology from President Obama a few years ago for this. And he showed, which is what Marletta had predicted, that they were very safe. sent it back again. I won't keep doing this, but he sent it back again, and the reviewer said, okay, but you know, it won't diffuse far enough to kill the remaining tumor. So Mark Saltzman, another one of my graduate students, who Yale asked found their biomedical engineering department, showed that it did diffuse far enough by different models, and he's been elected to 3 national academies. Showed that it did. Anyway, this kept going on and on. I won't keep doing this, but until 1996, when the FDA approved it. You can probably tell from the way I'm speaking that I'm very proud of how well all our students did, won all kinds of honors, got great positions, whereas the reviewers at the other universities, they haven't done so well. So let me just show you what this looks like. And I, again, apologize if anybody doesn't like the sight of blood, don't look. But here is a single wafer going into the brain. Usually they put 6 or 7 in and close up the brain. You know, it's very hard for me to give good advice when I give a talk. But a number of years ago, I remember I was lecturing in a chemistry and chemical engineering symposium at MIT, and I showed those slides, and my wife, Laura, came, and I asked her at the end of the talk, I said, what did you think? And she said, well, Bob, she said, the talk was all right. That is incredibly high praise, by the way. But she said, you know, you had those 2 bloody slides on for over 10 minutes, and you were telling every detail of the operation. She said, I don't know if you were looking, but all those poor chemists, they were turning green. So ever after that, I did what I said today. I gave a warning and showed them very quickly. But I just do want to briefly tell you the sequel to that, which was that about 2 years later, I got asked to give this dinner speech. But this was to a group of neurosurgeons, and I told them the same thing. And at the end of the talk, a number of the neurosurgeons came up to me and they said, you know, those 2 bloody slides you talked about? And I said, yes. They said, those were fine. They said, you could have kept those on as long as you wanted. They said, but those chemical formulas, you know, to put those on for a neurosurgeon after dinner, that's just awful. So anyhow, I sort of adjust how long I put these on. This was one of the early trials. Actually, it was done in Finland and Sweden, and shows that there's no cure, but it does show you you get a 5-fold improvement. And then, more recently, they've done studies, again, showing with 5,000 patients, 60 clinical trials, showing that it does statistically, improve survival. And this has now been used in over 30 countries, been FDA approved for the last 27 years. But maybe even more importantly,